introduction to stargazing. And one of the, I always sort of start with this blurb for the newcomers. And what this is really all about is learning your way around the sky. Every new month, we start a slightly different topic, so you don't have to build up on what we've done previously. The whole idea was basically to get together at the Queen Elizabeth Planetarium, newly refurbished, and chat about 2 or 3 topics, then head outside and look at the actual sky. But we can't do that, so we're going to do this from here. But as we move around the sky and look at objects, we will talk about different sorts of things like dark adaptation or the names of stars and things to see in the sky. And so every month we'll do pretty much a little bit of something different. And as we progress, well, essentially, you will have enough experience to earn a Explore the Universe certificate. And so with that in mind, that's what we're going to be doing tonight. We'll talk a little bit about the International Space Station because it's doing some nice passes. We'll talk about the navigation star, and then we'll talk a little bit about what Jupiter's doing, and a little bit on parallax, how astronomers measure distance. So with that in mind, I will go immediately to the start here. So this is a map of tonight's sky. Actually, it's tomorrow's sky. What am I saying? I'm ahead of myself. I planned for this, where we have in early evening being actually before 6 p.m. And so what we'll see here tomorrow evening is a path, assuming it's clear, which is very tough in November, as you've all come to realize. If this is your first year at looking at the evening sky in November, it's cloudy a lot. You have to really jump at the opportunities when you're given them. So the International Space Station will cross the southern sky, and these are from the Heavens Above site, and it's free. But if you actually register, then you can log in and it'll remember that you're from Edmonton and not 0 degrees north sitting on the equator in the mid-Atlantic somewhere, or the Eastern Atlantic. But tomorrow night, there's a really nice pass above Jupiter and Saturn. The charts default with south at the bottom, so you would hold the chart this way if you're looking into the southern sky. And the cool thing is it'll pass just above Mars and the moon at the end of his pass before it heads into the Earth's shadow. So it's, and we've got quite a few of these passes coming up. Let's see if I hit page down, it should come on. Not sure why that is not doing the appropriate page down for me. Sorry about that. So here are the next passes for the International Space Station. So for, again, tomorrow, just before 6 o'clock, and then a second pass at 7:30. For the newcomers, these most satellites orbit just about 400 kilometers up and circle the Earth once in 90 minutes, 90. Very different from the communication satellites, which sit out and orbit the Earth once a day and are called geostationaries. But these other ones, in summer, you can get 5 passes in one night of the International Space Station. But in the winter, with shadows coming sooner and the sun going down very early, we only get 1 or maybe 2 passes during the evening. And so we'll get quite a few nice passes. The brightnesses that you see here on the left are the magnitudes. The more negative means the brighter it is. And so generally all of these passes for Edmonton start in the southwest or west-southwest and cross the sky in the south before they disappear. And so the International Space Station is one of the brightest objects out there. It rivals Venus in its brightness, so you can't miss it once you do see it. Yeah, the heavens above is the best place to locate these things. Now, what I've done here deliberately is turn the map on its side. And the idea here is that if you're looking in the east, you can't quite see it because I've cropped it out, is the direction would be east. And so you would actually physically turn the map. So east is at the bottom while you are facing east. And so Mars would be high to the southeast. Overhead would still be the bright star Deneb, and the even brighter star Vega is going to be behind you overhead. But those are the sort of the 2 brightest stars, and then Altair being this is the summer triangle, is now coming past us, and the constellation of the month for me here is the W of Cassiopeia. Of Greek mythology, she's the queen, the mother of Andromeda, who got chained to the rocks. But the thing that I learned just recently is the star, whoops, sorry about that. I pressed a little too hard on my screen here. The star smack in the middle is called Navi, and I can now remember that because it's one of the navigation stars that we use. I don't think the name has got anything to do with navigation. I haven't actually looked it up, but that's the way I remember its name. The other name that you might find out here is Alpha of Cassiopeia, and that one I actually have to look up every now and then, and that's actually available. If you print out the Explore the Universe certificate, you can actually check what the names of the stars are. The main star is Schedar, Schedar, and it's one of the lesser known stars, but shows up if you're doing 3-star alignment on your telescope mounts. It'll sometimes say Schedar, so that's Alpha. But actually, one of I'll detour a little bit as I want to do, and typically the brightest star in any constellation is Alpha, then comes Beta being the second, Gamma the third brightest. So normally they're ranked in brightness, but sometimes, and Cassiopeia is one of them, is where they're ranked by position. So it's just from right to left in the constellation: Alpha, Beta, Gamma, Delta, Epsilon. And actually the same thing happens in the Big Dipper, currently in the north. You start at the bowl, at the end of the bowl, it's Alpha, Beta, Gamma, Delta, Epsilon, Eta, Zeta. Sometimes that's the way we work, but Alpha is the brightest in the constellation generally. So especially when you get to the smaller, fainter constellations like Triangulum, I cannot remember what the proper name of Alpha Trianguli is, but people will know what Alpha Trianguli, oh yeah, that's the brightest one. You know, Alpha Arietis, yeah, that's the brightest one. That's one of the ways we navigate around the sky, and remember names. So sometimes we remember them by their Greek letters more easily. Okay, one of the things coming up, which I'll touch very briefly about here, is the upcoming penumbral eclipse of the moon on November 30th. Now, the press tends to make big deals about the full moon, and especially if there's an eclipse. But I thought I'd try a simple analogy as to why this particular penumbral eclipse is underwhelming. Most people, if they would go out during the eclipse time, they would just look up and see the full moon and go, I don't see anything different. And the analogy is, what is happening is that the sun illuminates the moon, and then the Earth would come in and block, say, half of the sun. And so if in this analogy here, the left side of the screen is blocked, but you'll see that the moon is still completely illuminated. It's not as bright, as in it'll only be half as bright, but when it's sitting in a dark sky high up, you have very little reference, and your eyes adjust to the darkness so quickly that you're just about not likely to notice anything different at all. But having said that, this is a fairly deep eclipse, so instead of the sun being covered half from the moon, if you were standing on the moon looking back at the sun, about 3/4 of the sun will be covered, and you will end up in this penumbral eclipse. And on Fred Hispanic's webpage, Mr. Eclipse, that's one of his web pages, but eclipsewise.com, he actually has a picture of what this eclipse was like 18 years and 10 days ago. The eclipse cycles precisely on an 18-year, 10-day cycle called the Saros. And it's not quite exactly precisely, but extremely close to that. Anyways, this is what it looked like the last time, and this is just about exactly what it's going to look like again this upcoming Sunday night. So you'll see that the top area is fainter. It's not in shadow, because otherwise it would actually be just about black, but it's just dimmed considerably. If you keep tabs and if you're paying attention, you'll notice that, yeah, the north side is dimmer. But it's also happening, the peak, at 2:44 a.m. My recommendation is, do not set your alarm, stay in bed. The sleep will do you much better than having woken up and broken a nice sleep to see this thing. However, if you happen to be awake, stick your head towards the window and have a look, and you'll probably see something, but it's really not worth really disturbing your sleep for. I should just, before I go on here, oh yeah, this is where Berta comes in. But are there any questions on anything so far? Unmute yourself and ask away. Otherwise, I will start up Berta's presentation, and she's going to talk to us about, in this case, parallax. And Berta, just let me know when you want me to advance to the next slide.
Hi. Alistair and I were trying to decide what could be interesting to presenting here. And I know that when I am on deck at the observatory in the University of Alberta, I sometimes get a lot of questions from people regarding how do we measure distances in the universe. So I thought that maybe that should be something that people are wondering in here too. By we, I mean, how do astronomers measure? I'm not an astronomer myself. So maybe people here are wondering that too. So we thought it would be something interesting to bring to the conversation. Now, a little caveat here, as I say, I'm not an astronomer. This is not my field of expertise. This is something that I've learned myself. Recently, I knew a little bit about how to measure distances, but I by no means an expert. So if you have any question, just please let me know, but most likely I won't be able to answer. And so, but I can certainly research it and come back to you next week. So with that caveat in mind, please go ahead, Alistair. Well, first of all, there is not a single way of measuring distances in the universe. The universe is immense, it's vast in space. And so there are distances that are very short, like the solar system, and there are distances that are really far away, like far, far away galaxies, right? And so there is not a single way of measuring these just distances. And so there are different methods that can be applied at different distances, and some of them are maybe more accurate than others. But one thing to say is that all these methods are wonderful combinations of science and mathematics, and they are all a lot of fun and very clever. Please go ahead, Alistair. Thank you. So this is a little slide that basically shows, I don't know if you can see my mouse. Can you see my mouse as I move it?
No, that will be because you've given me the presentation.
Oh, yes. So can you please point to the center of the galaxy? That will be our galaxy, the Milky Way. All right. And so our sun, it's in one of the arms of the Milky Way. Can you please point to the sun, Alistair? Thank you very much. And so it's one of the arms of the Milky Way. So the first method of measuring distances in the universe is what is called parallax. Okay, and that originally basically could measure accurate distances to the first circle around the sun. And now with the introduction of the Hubble telescope and the Gaia space mission, you can use parallax to move to the second circle. So that's for you to understand the scale of the precise measurements of the distance of objects and stars within our galaxy, right? But the universe is, of course, there is way more than just our galaxy out there. So how do we measure out there? So today I will concentrate only in this parallax method that measures distances within a small range in our galaxy. And the next days I will move into different methods of how we measure nearby or close to us, relatively close to us galaxies, and then how do we measure distances farther away into space, into the universe, all right? But this slide basically shows an overview of the scales that we are talking about and how different methods can apply to different situations. All right, so if you can go to the next slide, I'm just saying that I just want to give a quick definition of what parallax means. So it's a very clever idea. Stellar parallax is basically the apparent shift of position of a nearby star against the background of distant objects. So Alistair, if you please point to the sun in the image. So we have the sun, and as the Earth moves around the sun along the year, we can look at a certain star, for example, the red dot in there, against distant stars. Okay, stars that are so far away that the parallax wouldn't work for them, and they look fixed in space. But stars that are a little bit closer, as the Earth is moving around the sun, can actually see that star moving with respect to the background of the stars as the year goes by. And so there are extreme positions in January and in July of that star moving. And just okay, let me mention quickly though that this is extremely exaggerated. We are talking about very, very, very small angles here, right? This is just for purpose of understanding, but the stars don't move that much with respect to the other stars. Okay, this is just an exaggeration. But the angle of movement of this star with respect to their stars that are fixed in the space because they're so far away that you don't see them moving, is called stellar parallax, okay? And so the distance, so the farther this star is, so the distance d from the sun to the star, it's inversely proportional to what is called, so the distance in parsecs is inversely proportional to the angle in arc seconds. And that's actually the definition of a parsec. We probably have heard this word a lot, a parsec, which is a measurement of distancing that astronomers use. And parsec is defined as the distance where a star moves an arc second through parallax. Okay, and so parsec, I don't think if I put it there, is equivalent to 3 point something light years. But astronomers use parsecs because parallax is used to measure the stars. And so this again works in is stars that are close enough to the sun that they actually you can see a variation in its position with respect to more distant stars along the year. And so the distance of the star in parseconds, d, is inversely proportional to the parallax angle in arc seconds. Okay, is this making sense? Is anyone would like me to go through something, or can we go to the next slide? Okay, no questions. So just a little quick history. Stellar parallax is actually so small, as I say, it was extremely exaggerated in that drawing. It's so small for the stars that are near enough that we can actually see something. It's actually so small that its absence, or the fact that people couldn't measure it, even though they tried, it was considered as actually previous to the 19th century, when it was actually the first time that parallax was measured. So prior to that, it was postulated, but it would actually not be measured, and people will use it as an argument to explain that the solar system is actually centered on the Earth instead of on the sun. They couldn't see the measurement of the stars. So they will say, well, because we don't see parallax, that means that the Earth is not moving, and so we are in the center of the universe.
Yeah, Berta, if I can add here, so yeah. the flip side to that argument is that if indeed there is parallax and the Earth is moving side to side, but it's just too small to measure, it would mean that the stars are ridiculously far away, too ridiculous to even consider. And of course, no, that is our universe. It's ridiculously large.
Yeah, that's correct. So, so just for reference, our nearest star, which is Proxima Centauri, which can be in the southern hemisphere, has a parallax of 0.7 arc seconds. So, you know, the universe, like this, the sphere is 360. You know, an arc second is really a small area, and so this is even smaller than an arc second. So can you even measure? How can you even measure that, right? But the first person who actually succeeded to measure the distance of a star using parallax was this gentleman in here, F.W. Wessel, who is a German citizen, who in 1838 measured the parallax of 61 Cygni in the constellation Cygnus as 0.28 arc seconds, which gives a distance of 3.57 parsecs. For this, again, I'm not expert. He used a device called a helio, I forgot, maybe you know, Alistair. It's a very clever device that has two mirrors, and so they can see a double image. Anyway, it's kind of like a telescope, but a little bit more complicated. Sorry, I cannot explain better, but yes. And so when it was proven that they could actually measure parallax, a lot of observatories started adding these kind of telescopes to their arsenal to be able to measure that. Now, in the 20th century, so nowadays, you don't need the special telescopes. You just, people started taking pictures. And so you take pictures, and first of all, they were using astrographs and photographic plates, and they will compare them with time, right, along the year. And you could actually measure. And later now with CCD cameras and computers, we can actually automatize this and create star catalogs of with their distances and the proper motion too. Does it make sense? Can we move? So, and this is just the last slide for today. So nowadays, as I say, people were doing it by hand with telescopes, one star at a time, you know, and creating their little catalogs, which is how astronomy did it in the past, when they will have these beautiful atlases of the sky. Every star was pointed there by hand. Nowadays, in 1999, one of the first the satellite Hipparcos was actually launched to measure and to create a catalog of the sky, basically by taking photographs and with the CCD camera. And they could measure stars that were about 1,600 light years away. But not all. I think it also depends on the brightness and the color of the star that this method is, and the proper motion of the star, that this method is actually more or less reliable. So that doesn't mean that you can measure every single star that is closer than that. I think it's still complicated. And so the Hubble telescope has a much better precision in measuring the arctigrades than the satellite Hipparcos. And so they were able to reliably measure distances of up to 10,000 light years for a small number of stars. Again, it depends on the brightness and the color of the star and the proper motion of the star that you can actually measure with more precision or less precision their distance. But again, if you remember that the drawing that I showed you at the very beginning, we are still talking about distances within our galaxy. We are not even outside of the galaxy just yet. And now currently there is another mission called Gaia, which is from the European Space Agency, and is still currently taking data. They released first catalog of stars. They are now in their second catalog of stars, and they are getting, this is the best and more accurate yet catalog of all the nearby stars that we have, which is being provided by this Gaia mission, which I read today is gonna still take data until 2022. So that's for today. That's about parallax, which is basically how we measure distances within our galaxy, and not even on the other side of the galaxy, like only in our area, in our local area.
Thank you, Berta.
Okay, you're welcome.
Okay. The next little segment is talking about the time cycle of Jupiter's orbit. And so here is a view of the inner solar system, well, extending out to Saturn. So Earth is the little blue circle, and here the sun is smack in the middle. Earth is here. And so this is a sort of a well, computerized snapshot of if you were above the solar system looking down, as everything turns counterclockwise from our perspective up here. And if you're looking down, this is where the planets would be. And so in the summer, when Jupiter and Saturn were in the south, due south at midnight, this is essentially their alignment. So Jupiter is to the right of Saturn. If you imagine looking along this line, Saturn will be just a little bit to the left. Now Jupiter takes almost 12 years to do a full circle of the solar system. So its year is 12 years. And Saturn is even longer at 29 and a bit. And I just find it easier to remember 12 and 30. The 12 years seems like a fairly long time, but Saturn at 30, if you can imagine 2 orbits of Saturn at 60 years is essentially, well, that's a lifetime of somebody back in the first age of great civilizations of Greece and Italy. So it's no surprise that the name of Saturn in Greek is Chronos, which has some of its roots in the word time, as in chronometer. So that's why Saturn is named that. But it's also, there's the mythology is mixed, and apparently it was confusing back then because Jupiter's father was named Kronos, but without the H. So the thing about father time kind of got blurred back then. The sort of the mythology works out real nice that Jupiter, being Zeus on the Roman side, was the biggest planet, the most powerful of the gods, so it gets the brightest planet out there, not counting Venus. And so essentially it takes, well, as I said, 12 years for Jupiter to do a full cycle. So in 1 year's time, we come back and Earth has returned to its spot in 1 year, but Jupiter has only moved 1/12 of the way around the circle, Saturn even less because it's going more slowly. And so the neat, simple thing to remember is, well, we have 12 months of the year, 12 zodiacal constellations that the sun moves through. And so it's essentially 1 year per constellation. Now, as you all know, the constellations aren't equally sized, but on average, that's about 1 year per constellation. And so Jupiter currently is sitting in Sagittarius, and by next year, when we come around, it will be in Capricornus, while Saturn will be sort of trailing behind it. And as you may have noticed in the sky, how quickly the two seem to be approaching each other. So essentially Jupiter, I've stepped back here, is about to overtake Saturn on the solar system racetrack, as I like to call it. And so Jupiter will be on the right of Saturn in the next few nights. By December 21st, they will be quite close together, and every day and month thereafter, Jupiter will be moving more and more away from Saturn. So in 1 year, it'll be just about a full constellation over to the side of Saturn. And then, and so, for us, the difference though is that Jupiter was at its peak in July last year, but because it's moved on, it's going to take Earth another month to line back up with the sun again. So a straight line between the sun, the Earth, and Jupiter when it reaches opposition. And we call it opposition because it is opposite the sun at that time. So that will be mid-August of the upcoming year. And then a full 12 years later, Jupiter will have done a full circle and we'll be back in Sagittarius again. And you know, oh yes, and this is, I remember very clearly the first time I ever saw Jupiter. It was sitting in Aries, and 12 years later when it came back, it was just a sudden, that's where I first saw it. And so hopefully, if you first saw Jupiter tonight, this past summer sitting in Sagittarius, well, 12 years from now, you're going to get that aha moment when you see Jupiter back in the spot where you first realized that, yes, that's what that is. But that said, in 12 years, where Saturn is going to be, it's going to be essentially in the winter sky almost 6 months, because Jupiter takes 6 months to come around. So from summer to winter, Saturn is going to be in the late late winter sky by the time Jupiter comes back 12 years from now. And so, of course, the next question you then might ask is, well, how long does it take for Jupiter to catch up to Saturn again? And so that they'll be both together. And so it's similar to the hands of a clock where both hands are moving, but one moves faster than the other. So by the time the hour hand catches up to, sorry, the minute hand does its full circle and catches up to the hour hand, the hour has moved on a bit. So it actually moves a bit like that, but faster. And it takes 20 years for Jupiter to catch up to Saturn. And then from Earth's point of view, Jupiter will once again be overtaking Saturn in 20 years, so 2040. So, but they'll now be in a different part of the sky. Instead of being in the south at summertime, they will be in Virgo in the springtime when they overlap. And 20 years farther into the future, 2060, or if you want to go sort of backwards, the year 2000, the millennium, Jupiter and Saturn were both together in Taurus, quite close to the bright reddish star Aldebaran and the Pleiades. So Bruce kind of coined that as the Millennium Diamond, where you had four amazing objects right close to each other: Jupiter, Saturn, Aldebaran, and the Pleiades. But we won't get to see that for another 40 years from this year. So that's the time scale of the solar system. So it was also pretty cool for me a few years ago to see Saturn back to the same spot when I first came across it. It was quite near the Beehive cluster, although I had no idea the Beehive cluster was there. But I knew it was in Cancer based on a map that came in the National Geographic. Went outside and there's this bright star where there are no other bright stars. That was Saturn. So you get to do that, and it brings back those early memories really nicely. That's this segment. I'm about to move on to the next one. Are there any questions? Okay, hearing none. Berta thought it would be a really good idea to talk a little bit about sundogs, because we had some the other day. And so here's a little segment about where sundogs come from. So these are typically, you'll see them most commonly in the daytime sky, although you can see moon dogs. And they're called that because they stay exactly the same distance on either leading the sun or following the sun, just like a dog would either lead or follow its owner. So sundogs is the common name for them. And here's a solitary sundog. Off, in this case, it would be off to the left of the sun. The inner edge is always red and the outer edge is blue. But if things are not perfectly uniform, the light gets smooshed out on the blue side and gets washed out a bit. But I had a question from one of our newer members that said, hang on a second, it's +3. How are those things ice crystals that are causing this? And how do you even see them in summer if it's +20 or +30? And the trick is that the upper atmosphere, where the cirrus clouds and ice crystals form, is actually quite cold. You may remember when, if you've had a plane trip, maybe not recently, and the captain used to come on and say, we are flying at 40,000 feet, and outside your window it is currently -50 degrees Celsius. Now, of course, we get those on our little displays in the back of the seat in front of us, telling us what the temperature is and how high we are. But this is the temperature structure average of the Earth's atmosphere. And so we start, mid-latitudes, In summer, it's 10, 15 degrees, and then the temperature ramps off. If you've ever done mountain climbing, you'll know that the temperature is cooler at the mountaintop than it is down below. But if you kept on going higher and higher, the temperature would continue dropping until you've got to minus 40 or thereabouts. And this diagram has it about minus 58 or so, but that'll depend on where you are and the time of year precisely, but overall it's down in the minus 40s to minus 50s. And then above, at that point where the planes fly, you'll know that there's not many clouds anymore, and you're into the tropopause. And jet fighter craft fly at that higher level. And then above that, it's just clear, thinner and thinner and thinner air. But the temperature does climb back up a little bit. But even in the heart of summer above us, it's minus 40. And so we get ice crystals. And so any of the wispy clouds are typically ice crystals. And the vapor trails that come out of the rear engines of planes or cars in winter, when you see the puffing out there, that's all water vapor. So that's actually droplets, liquid droplets of water. But if it's cold enough, eventually they freeze, and just depending on the precise temperature and humidity, you get ice crystals forming. Sometimes they're very small and round, but most of the time ice it has a very geometric structure, and it's all six-sided hexagons. And so there are two main types of ice crystals that form. One of them is, here at lower left, is called a pencil crystal, because if you just imagine a pencil, yep, that's what a part of a pencil looks like. So we call them pencil crystals. But that's what very small, and very small is a millimeter or less. So much, much smaller than a typical snowflake, because a snowflake itself is typically made up of hundreds of tinier crystals. And these ice crystals are typically transparent, and so light passes through them just as it would through glass or a glass prism, and split the colors, like your Dark Side of the Moon album cover splits white light into a rainbow. And that's essentially how our halos form, and why they're red on the inside and blue on the outside. But you can also have not just these long pencil crystals, but you can also have what we call these plate crystals, where they're called a plate crystal because they're fairly wide compared to how thick they are. So a plate is pretty thin, just like a dinner plate. And so that's pretty typical. And when you do the math of how refraction works through a block of, whether it's ice or glass, for ice, that angle for the red light coming through is 22 degrees. So you'll often hear me say something about, oh, we've had a great 22-degree halo today. And that's the size of this circle from, if you measured the angle from the sun to the edge of the circle, it would be 22 degrees. And so that's just about, as you can see, if you hold your hand up from the base of your palm to the tips of your fingers, is pretty close to 20 degrees. And so the sundogs also lead or follow by the same amount, 22 degrees. Now, it's not precisely, because it turns out that the values actually change slightly depending on how high the sun is above the horizon. And some of the forms of the halos, going from perfect circles, if you have these pencil crystals, but if you happen to have big pencil crystals, instead of them floating randomly, they tend to float horizontally, with the long side, like a pencil on a table is horizontal. the more horizontal they are, the more you get this other type of halo. And these ones are called upper tangent and lower tangent arcs. And depending on the height of the sun above the horizon, that shape will gradually change. And so once you actually start to get used to looking for these halos, and it's always, if you can, use sunglasses to help cut down the light, and especially put the sun behind your hand or behind the edge of a building. Otherwise you tear up pretty quickly. But quite often I've seen this halo where people would say, oh, I saw a 22-degree halo, but I didn't see the sides of it. It was only really at the top or the bottom. And it's well, they're actually seeing a halo for the upper and lower tangent arcs. The other thing to look for that happens, especially in our climate here in the Great White North, is that plate crystals are very common when it gets cold and you just have a -20 or especially -30-degree day. All of the humidity coming out of our furnaces and the boilers for heating, all that vapor crystallizes out, and it's really low. It stays down quite close to the ground, but the plate crystals are the ones that form most commonly. And what you tend to see are the sundogs on either side. You can see there's barely a 22-degree halo here. There's a bit of an upper tangent arc, and then way, way high in the sky is this other halo here called a circumzenithal arc, because it makes a circle around the zenith. If you actually took and you could extend it all the way around. It doesn't actually do that in nature, but that's the one, if you could, it would make a circle where the center is directly overhead at the zenith. But there are other arcs in here as well. If you get the right condition, you can actually see there's a bit of an arc here. And if it's perfectly circular, it's a 46-degree halo, but otherwise it becomes yet another form of arc, and it's a supralateral arc, if you're keen on the names. And not seen here are, you sometimes get the other ones, which would be down here and down here, if you sort of can imagine continuing that circle, but down below you would get that. And the other thing to look for is these sundogs. Often they have extended long lines, and you can see part of this line going all the way off to the side here, and that's called a parhelic circle. So even in patches of cirrus, you can sometimes see these, and they can be fairly fleeting. Sometimes you only get 10 minutes and it's nice, and then it just kind of dissolves as the upper atmospheric conditions are such that sometimes the ice crystals are solid white, opaque, like ice can be. There's light can't get through it. But you'll notice as well, the key to looking for halos, once you get used to them, is whenever you see a sky that's not blue, where it's this, yeah, I mean, this is generally bluish, but it's there's a sort of a gauze or a thin film of stuff in the sky, and that's the best time to look for halos. And the same thing for around the moon, you can get these. So one of the other very common ice crystal shows that we get here, and this is the last one I'll be talking about, are called pillars. And once you see the picture that I show, well, I may as well advance it for the moment. You'll sometimes see just below, or sorry, above the setting sun or above the rising sun, you'll sometimes see this pillar. And more commonly, You see them around, especially the industrial areas of town where there's a lot of moisture production coming out from the factories. Anything that runs heat creates moisture. The power plants and of course Refinery Row uses a lot of water in their production, and it goes out, crystallizes, and if it's just right, you get these pillars. And they're different colors because they reflect, since they actually are reflecting the light, they take on the light of whatever their light source is. They take on the color of their light source. So red traffic lights, you'll get a red pillar. Green traffic lights, you get a green pillar. And so how do those form? Oh, these are the plate crystals seen here from the side. From your perspective, you're looking at low in the sky at these through the plate crystals, but the light source will reflect off the bottom. This particular light ray, you won't see anything. It's only the ones that reflect at the right angle back to your eye. And from your perspective, the eye and brain just project. You just add up all those light bits of light, and it looks like a pillar. And one of the times I remembered way back when I was observing, at one point it was a clear sky, it was about -20, and it was like, oh, we've got aurora. There's an auroral spike there, and then it's not moving. No, it hasn't moved at all. And then realized once we noticed that in our eyepieces, they were collecting tiny crystals, we suddenly realized, they're ice crystal pillars, not aurora spikes. And so that's something to look out for this winter, is pillars, all these arcs, upper tangent arcs, and the sundogs. And especially you'll see these sundogs, either they can come from cirrus or from the jet contrails that crystallize out. So yeah, very beautiful phenomenon once you twig into them and start looking. So that is all the topics we have for tonight. I'll thank you for listening in, and I'll stop sharing my screen, and we'll go into gallery mode here, and we'll take any questions you might have.
I just want to say thanks a lot for the presentation, Alistair and Berta. That was pretty interesting, especially the bits about parallax. I'm hoping to someday be able to actually get an image of stellar parallax. I think you said 61 Cygni was about 0.2 something arc seconds. Do you think that would be doable by just an amateur astronomer?
Well, go ahead, Berta.
Oh, I wouldn't. I just wanted to actually, I was thinking, Alistair, you probably know how much the moon covers in how many arc degrees is?
Yeah, the moon is 30 arc minutes. And so 1 arc minute is a bit bigger than the disk of Jupiter. So Jupiter's disk is on average sort of 40 arc seconds. So 1 arc second is, you know, actually the moons of Jupiter are about an arc second and a half. But of course, it's the shift back and forth that you actually are trying to measure. So it's pretty tough going. But you got to remember, it's like, well, hang on, if they were able to do this in the 18th century with, you know, it's industrial age stuff. It's just like we ought to be able to do that nowadays, but getting, well, as you know, sub-arc second seeing, where the atmosphere is blurring and moving things around, getting a half an arc second is really tough. So it's still mind-boggling that they were able to get that level of precision. And as Berta had talked a little bit about, they had some pretty fancy-dancy telescopes to measure that. And one of them is a split objective. And Berta was talking about how they had two of them. And I can't quite remember how they do it, but they somehow split the image, get two, and then they can measure it a little more precisely than usual. But I read a really good book. It was published about 25 years ago, but it's called Parallax, and it has the whole history of measuring the distances to the first stars, and it's quite interesting. Because one of the things that they actually encounter, and it's a totally different subject, is called aberration. And it's what ends up happening is that, well, it's really obvious if you're sailing, but if you're, say, running, as in jogging on the street, if there was no wind at all, you would feel a wind in your face. If the wind was coming from the side, well, actually, we all know it. If you've got an umbrella and you're walking in the rain, you have to tilt the umbrella forward because it seems the rain is coming in at an angle. Well, the same thing happens with the Earth going around the sun, is that the stars appear to come from a slightly different direction than they do. And it's about the same size as measuring parallax. So, I mean, that'd be still a pretty cool.
Yes, and also I would like to add to this, Abdur, that if you notice what they use nowadays, Hipparcos, Hubble, and Gaia are outside of the atmosphere. But that being said, they did measure, I think I read today before Hipparcos, there were already a catalog of 100 and 150 stars where they knew their parallax. And that was done in Earth telescopes in the old times where they were taking these plates, and they could check the stars. So I'm certainly not discouraging you, and considering your tenacity and your skills, like Alistair said, you have to wait probably for very good seeing nights. But all the astrophotographers in there, including Josephine, it's a wonderful challenge to try and measure the parallax, I would say.
Of course, the reference to check is the Observer's Handbook. And there's a few pages that talk about the stars, and a couple of pages within that talk about the nearest stars. And they have a table of the, is it 50? No, 30. Yeah, the 50 nearest stars and what their parallaxes are. And it turns out the other sort of famous star other than Proxima Centauri is Barnard's star, is well known. That's down in Ophiuchus, but its parallax, according to this, is 0.5 arc seconds. So that's probably the one to go for first, is Barnard's star. But yeah, the next closest ones are a whole bunch of these tiny red dwarfs that we've only discovered in the last 100 years. The Wolf 359, Lalande. Sirius is actually fairly close, 0.37 arc seconds. But I presume Bessel did not go for Sirius because it's so bright that they probably had trouble measuring it. But the other reason he went for 61 Cygni is that it's a binary. And so I think that was because both of them were moving. They knew that 61 Cygni was moving, but the trick is, as it's moving, it's kind of going back and forth, that it would be easier to measure accurately compared to just a star by itself.
Mm-hmm. And another thing to notice though is that the stars do have proper motion too, right? So you have to, I don't know how they did compensate for that, but there needs to be, yeah.
Yeah, in this book, they also talk about John Herschel going to South Africa and measuring Alpha Centauri, and then it's the just like, so, you know, what are your measurements? And it's just, you know, 0.8 arc seconds. How accurate are your measurements? 0.8 arc seconds. So it's a, you know, it's like having a ruler, you know, with 1 millimeter ticks, and just like, how accurately can you measure with that? And it's like a millimeter. So
thanks, guys.
Yeah.
You might find it easier imaging those Einstein ring arcs around.
Yeah. That's still a work in progress, so still working on that now. But I think 0.5 arc seconds might be doable. Then I might try Bernard star, because I've seen details on Mars smaller than 0.5 arc seconds. So I think with some like speckle imaging or something like that, I think maybe Bernard star might be a viable target. So if anyone's looking to try it out.
I mean, you should be able to notice it move over at least, you know, 1 year. It should show if you're zoomed all the way in and down to the.
Yeah,
the
that has pretty high proper motion as well, I believe, right? I think it's one of the ones with the largest proper motion.
Yeah,
yeah, it has the highest proper motion of any star that we know of.
Oh, that should be interesting.
Is it here? That's also in that table of stars. Where is it? Yeah, Barnard star. If I can get that right. There we go. Proper motion is 10 arc seconds.
So that's per year?
Yeah, 10 arc seconds per year.
Oh, well, that should be easy enough to notice then.
Yeah, no, that's pretty reasonable. So, anyways, yeah, well, thanks again for hanging around, and if you have any suggestions, please send them in, pop them on the Facebook page that, hey, you haven't talked about this topic yet. You know, let me know. As I sort of mentioned at most of the introductions, about every year or so we'll be coming full circle and starting over with some of the topics that we began with last year. But every year, I guess, is going to be slightly different. We'll be inspired by whatever happens to be out in the sky as to tilting which way we go with the topic at hand. So with that, I wish everyone a pleasant evening. And we will not be doing this 1 month from now, because it's like it's not quite Christmas Eve, but it's the 23rd, and will be I think a time to take a little pause, but we'll be back in later January. And also remember to tune in exactly 1 week from tonight for Jeff's What's Up in the Sky this month. And I'm sure Jupiter and Saturn will be on there. And
yep, Jupiter and Saturn will be there. Meteor shower, and I haven't quite decided which constellation to talk about. I was thinking maybe talking about the Christmas star, but I might piss a whole bunch of people off, so maybe I'll just leave that one.
Yeah, I'm looking forward to a repeat of the that 4 BC gathering where it's you had Jupiter, Saturn, Venus, I think Mars, Mercury, and the crescent moon all fairly close, not overlapping by any means, but it would have, even the most casual sky gazer would have been, whoa, what is happening with all that stuff there?
Yeah. Well, I was thinking of playing a clip from Monty Python and the Life of Brian about what are you doing creeping around at 2 o'clock in the morning? It doesn't seem very wise to me. Anyway, we'll see.
Nice.
All right then. Pee off.
He's not the Messiah. He's a very naughty boy.
So,
You guys have a second career.
Yeah.
Hey guys, have a good
have a
night.
good evening. And
All right. Thank you.
that's some of the stuff you'll hear if you come out meteor observing with us. While we're waiting for the next meteor.
Yeah.
Anyways, have a good evening, everyone.
Yeah.
Good night.
Thanks,
Good
Alistair.
job. Thanks, Alistair. Good job.